Well, hello and welcome YouTube. Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. If you step on inside, guys, we're going to continue our quadratic factoring methods. Now, I've graphed out of vertex form and factored form, and we've converted from standard form to vertex form by completing the square, and from standard form to factored form just by factoring. And now I'm going to graph out a standard form today, and I'm going to convert all three forms with you together, including going from vertex and factored form to standard form. A standard form really is the intermediary of the other two. You can go from standard form easily from vertex to vertex and factored form, and easily from factored and vertex form to standard form. If I want to go from factored to vertex, I want to go to standard form in between, and vice versa. But you can also graph out a standard form, and as always, all these have their own unique features. Obviously, vertex form, you can find the vertex with it. The numbers reveal the vertex. Factored form, you reveal your x-intercepts. They all reveal stretch factor, by the way. In standard form, you can get the vertex out of it. You have to calculate something with it. And you have your y-intercept. And, of course, stretch factor. And for this sheet here, I'm sure its intent... This sheet is not originally mine. This sheet wasn't actually intended to graph with, just to transform equations. But what I'm going to ask to do is identify and find the standard form in all three of, among all three forms. Let's find the standard form, and let's always graph using that one, because we've practiced the other ones. So in this one here, I'm going to take this equation, this is standard form, and I'm going to use the information provided to construct the graph out of it. And then I'll confirm in vertex and factored form that it is indeed what I was looking for. And then in number 2, this is clearly vertex form, so I'm going to use what I get in standard form, this one, in order to graph that one. And then number 3, same thing, I'm in factored form here, and I'm going to use the standard form thing that I get out of this one as well. I made a really weird, like, swallowing noise. And then numbers 4, 5, and 6, there's the graphs I'm going to be drawing them on. And then numbers 4, 5, and 6, I'm going to be doing the same thing. We got a standard form here, I'm going to be graphing out of that. Then I'm going to get into standard form here from vertex form in number 5. And number 6, I'm going to get the standard form out as well from this factored form and do the same. And like I said, I'm just going to confirm that everything I got in vertex form was as anticipated, and factored form, that they match the graphs we had. So a lot of switching back and forth on slides. I hope that's okay. Only 6 problems on here, and they'll have all the graphs there with you. So I'm just going to go ahead and get started, guys. Now, as far as standard form goes, it is y equals ax squared plus bx plus c. Again, the highlight here will be standard form and what I can do out of it, or how I can get into standard form, okay? Now, the A is the stretch factor as before, the vertical stretch factor. The C value is your y-intercept, and I did tease this before when we were in factored form because I went from standard form to factored form, so I showed you how that C value applied and the idea of that. Now, B has no very specific, at least not for the actual graph itself. There are some things to it, but the number itself doesn't lend to anything specifically with the graph except what we can calculate out from it and the A value. And it is that your vertex is found at negative b over 2a for the x value, and the y value, of course, you substitute whatever you got for the x value. So this says f of negative b over 2a, as in whatever I get here, I plug it into my equation to get my y. And that's how you can get any point on this graph, by the way, guys. If I want to figure out what the y value is when x equals 100, I substitute 100 in there. And if my vertex is 100, that's exactly what I'm going to plug in. I sure hope it's not going to be 100, because then I couldn't fit it on here for any of these graphs. But that's the information that we get out of this. Okay, that's all the information there. Negative b over 2a obviously is a starting point, as well as that y-intercept. I'll just kind of keep that in mind, and I'll write out that information. So let's go and get started, guys, on number 1. Number 1, y equals x squared minus 6x minus 7. The y-intercept here on number 1, that dot kind of keeps, hold on, it's kind of OCD. There we go. The y-intercept on number 1 is at 0, negative 7. Again, the c value is the y-intercept there. So I can already plot that point here on number 1. This isn't necessarily the vertex. In fact, it's not the vertex. Just don't assume that this is where we do symmetry from. Symmetry will be from the vertex value, which is going to be negative b over 2a. So if the a value, of course, is 1 right here, right? That's a 1, and the b is negative 6. For the vertex, guys, the x value will be at negative b over 2a, like so. The opposite of negative 6 is positive 6. 2 times 1 is 2, and there we are left with 3. So 3 is the x value of the vertex, and the y value of the vertex is going to be by substituting 3 into this equation. So what is essentially f of 3? Well, we're going to get 3 squared minus 6 times 3 minus 7, which is 9 minus 18 minus 7, which is negative 9 minus 7, that's negative 16. So your vertex is at 3 comma negative 16. Totally fitable. By the way, I haven't looked at these problems hard enough to make sure they all fit on these graph things. This one just fits, and it just so happens to be because I have such tall graphs here. I'm going to double check and see that these all actually fit. I mean, as we graph them together, I really apologize if they don't. I'm going to have to make amends for it and say we have to shift the scale by 2s or something like that. So we're going to be at 3 negative 16 right here. There's the vertex x value. Now, as far as the other points go, guys, you can do what you need to get them. One of the things that we can do here is kind of like draw our axis of symmetry here at x equals 3 and reflect the y-intercept across. But as I would definitely require any student to do, at least get 5 points on a parabola. So you don't start drawing absolute value shapes or something else that's not a U-shape, parabolic shape. I'm always going to plot as many points as I can fit, or as many points as are reasonable, like no 1/64th kinds of fractions. This is a stretch factor of 1, guys. The a value is 1, and if I want to plot more points, I'm just probably going to utilize the stretch factor to get the rest of them. So let's see. We got 1, 1. Now, by the way, this is assuming you've seen some of my previous things, like graphing out a vertex in factored form. I assume you've seen those when it comes to me saying 1, 1. What I mean by that is you go 1 away from the vertex, you go up 1 squared. You go 2 away, you go up 2 squared. You go 3 away, you go up 3 squared, and that's that point right there. That's 9 up. You go 4 away, up 4 squared, and we're going to hit our x-intercept right there. And by the way, we reflect these points across as well. And I'm actually going to fit one more point up here, I believe. 5 over is up 5 squared. We're at negative 16 right now. So 25 up from negative 16 is positive 9. So that's all the way up right here. And I can reflect that point across as well. So, whoops, that's not quite a reflection. That would be a reflection. See my reflection. All right. And let's get a... See, this allows me to get kind of the U shape I'm looking for. You might call this a V shape, but this is a slow curve outward. And it does that. Now, I don't know, I'm not certain whether or not whether the standard form graphs here do what I want them to do as far as, I don't know if any of them have a values that are fractions. I really want to dive into some of the fraction ones if I'm able to. This is not, I'm trying to select, hold on, I'm trying to select this, there it goes. I'm trying to select that axis of symmetry that whole time right there. All right, so there's the graph for that one on number 1. That's graphing out of standard form. Of course, I will do that for all of the problems. I'll graph out of standard form. However, I still want the vertex form equivalent and factored form equivalent. So let's go ahead and get those two. Let me move myself over. So on number 1 here, the vertex form, I'll do in green here. So vertex form is, what we do is we take the equation and we will complete the square on it. We take the first 2 terms right here, leave some space, and whatever I do to one side, I have to, whatever I do right here, whatever I add, I have to subtract on the same side of the equation. This is, again, a lot of the stuff, guys, is assuming you've done this before. So completing the square means taking this term here, dividing it by 2 and squaring it, and I get 9. And then taking this, that 9 right there, I'm also going to subtract over there as well. Okay. Now this guy factors down to x minus 3 quantity squared. So y equals x minus 3 quantity squared like that. And negative 7 minus 9 is negative 16. So that will be this equation here. Y equals x minus 3 quantity squared minus 16. And that seems to confirm the vertex that we got here at 3, negative 16. Now, I'll tell you what. You don't have to get vertex form by completing the square. If you noticed, we did get the h and k vertex values by using negative b over 2a. It's possible to use negative b over 2a to find these values and then plug them into your vertex form equation as you know it's supposed to, work. So you can do that. My purpose of what I'm doing right now is getting vertex form the way that we know how to by completing the square to confirm that the negative b over 2a that we got was correct. Later, if you know how to do negative b over 2a and you're sure that you're getting them correct, then you can use that negative b over 2a version to get the vertex and put it in vertex form. So if you were ever asked to come up with the vertex of your quadratic equation that's written in standard form, you can either complete the square or use negative b over 2a to get your values and then plug them into your x minus h plus k scenario. Either or works, but for what we're doing, we're confirming, and we're going to do it 6 times or whatever, we're confirming that we can also convert to vertex form by completing the square and trust that our negative b over 2a that we got was correct. I hope you know what I mean by that, guys. I'm giving you that idea of, did we do it right? You know what I mean? Just like, you know, for example, factored form. I could look at my graph and tell you where factored form is because my graph hits the x-intercepts and the x-intercepts represent factored form. But what I'd rather do is factor this equation right now and see if that matches the x-intercepts that I got in my graph, you know, so I have no like bias toward just saying, oh, those must be the factors in factored form. Let's see if we can algebraically do it. So I hope that's making sense what I'm saying. Okay, so let's do factored form right now, and I'm going to do that in purple. Sorry for the spiel there. So what we're going to do, straight up, guys, I have really no work to show, that if this is factorable here, we got to find two numbers that multiply to make -7 and add to make -6. And that's going to be -7 and +1. So that's my factored form right there. I really can just write it right here. There's really no work to show on those ones. Sometimes there can be if there's a common factor, but not here. There's the factored form. So the anticipation for this, y'all, if you remember, is that the intercepts, when you set y equal to 0 and use zero product property, that either x equals 7 as an x-intercept or x equals -1. Is that the points that we got on this graph here? Yes, this is x equals 7 and x equals -1. Those are it. And of course, we found vertex out of factored form by, if I move myself here, by finding the axis of symmetry in between. I know this is more of a standard form thing. I'm not going to talk about this one in future ones. But the standard, vertex is right in the middle of these two things right here. That's 4 away and 4 away. And then you plug in that x value and you find it. So all these are interconnected. They all have their own little benefits and stuff. And you can use any one at any time, assuming it's factorable and assuming you want to. But today's practice is standard form. So let's move on to number 2. Now, number 2, I want to get into standard form first because I'm asking to graph out of standard form. That's cool. So what I'm going to do is I'm going to take this equation, and getting it in standard form really means, guys, if you look at it, standard form is no parentheses. Where is it? Standard form is no parentheses. All like terms would be combined. You know, literally in standard form, the leading degree is the the quadratic. Is 2, so the leading term is the quadratic. So what I want to do is I want to just basically expand this thing. I am going to use the order of operations properly. Here's what you don't do. Here's what you don't do. You do not distribute the 3 into this guy right here. There are 2 reasons that we can talk about there, but you don't distribute the 3 right here for one reason, order of operations. We do exponents before we do multiplication. So that's the first thing, okay? So as far as standard form goes, I'm first going to expand this. And listen, guys, I'm going to, I'm going to show you this first. This is x minus 1 times x minus 1. That's the expanded version, because I also want to show you this. Once again, you may distribute the 3 into one of these like that. You would not distribute the 3 into both of these like that. Okay, that would be the same thing as distributing the 3 into that and doing, no, multiplication only occurs once, if that makes sense. If I do 2 times 3 times 4, I don't do 2 times 3 and 2 times 4, like that. I do 2 times 3 and then times 4. So same thing. What I would recommend really is just foiling this part out, expanding that, and then distributing the 3 afterward. So this will be x squared minus 1x is minus 2x, and then -1 times -1 is +1, and then minus 3. Now, what I'm going to do in the future on the only other problem where we do have a vertex form to expand it, is I'm going to expand this like a perfect square trinomial. You square the first term, you square the last term, and you double the product of the x and -1. And that's what you get. I don't have to write this part out, Just don't do, and also don't do this, guys. Obviously, it's not x squared minus 1 squared, right? That's not how that expands out either. So just giving you all the warnings. These are things of old. I mean really old. I mean a couple months old now. So that's that. Anyway, now I can distribute the 3 here, and I get y equals 3x squared minus 6x plus 3. And there's a minus 3 there as well, right? I want to make sure I did that correctly because, oh, sorry, this is a different problem. I was going to say, because I don't remember this graph having this. 3 minus 3 is 0. So this is just going to be y equals 3x squared minus 6x. And that's the standard form right here. Y equals 3x squared minus 6x, okay? Okay, so there's that. Standard form. I'll get factored form later. I want to first, I'm going to graph out of standard form. That was my whole goal. So in standard form, the vertex of standard form here, the x value is going to be negative b over 2a. So the b is negative 6 again like last time, only this time the a is a 3. So negative b over 2a. That's 6 over 6, which is 1. So the x value of the vertex is 1. And the y value of the vertex is obtained by substituting 1 into the x values here. So it's 3 times 1 squared minus 6 times 1. Give me 1 second here. Okay, I just want to make sure I was recording, because sometimes if I wasn't recording, I'd flip. Well, then I'd know to stop recording. 1 squared, so here's order of operations again, guys. We do 1 squared first. 1 squared is 1, times 3 is 3, and then minus 6 times 1 is negative 6. So negative 3 is the y value. So your vertex is at 1, negative 3. And that's where I'm going to first plot this point here. So I'm going to start at 1, negative 3 like that. So I guess these will all be blue because I just want to kind of show that I'm emphasizing my standard form bit. Sorry if it's a little colorblind there. And, you know, I could just use the stretch factor to get the rest. One other point I just want to get you for sure is identifying the fact that this was, when these 3's canceled out here, guys, this was a plus 0. That means your y-intercept is 0. You know, so it crosses at the origin here. You know, we cross at 0, 0 like that. And if this is our vertex, right, if this is our axis of symmetry right here, then that must also mean that we, you know, reflect across that point there right here. And that's another point. And, you know, this all but confirms what we were just doing when it comes to stretch factor. You guys know what our stretch factor on this was? It's 3. It's 3. It's 3. Our stretch factor is 3. Vertical stretch factor, which means instead of going 1, 1, 2, 4, 3, 9, 4, 16, we're going to triple those heights. So we're not going to go 1, 1, we'll go 1, 3. We won't go 2, 4, we'll go 2, 12. I don't think the next one will fit, but instead of 3, 9, we'll go 3, 27. So we're going to triple our values. And so let's see if that actually works out for the first one. Instead of 1, 1, we'll go 1, 3. Well, there it is, right? That seems to fit with what we were doing. 2, 4, we'll go to 12, triple the 4. Negative 3 plus 12 is 9. So we're going up right there like that and reflect that over. And again, that's really all I can fit when it comes to this graph here. So I'm going to go ahead and draw the graph based on that best I could. Never go full vertical there and bring our way down. Remember, the next one will be 27 up from our vertex there, so I can't imagine that. That's not done very well. I really shouldn't be picky, but I really want to emphasize that you should. This is just, I can't do this well because I'm not on paper, and I'm kind of drawing on a tablet that's like not right on the screen or anything like that. You guys know that tangibly on your paper is probably much better there. But never go full vertical, and that's good enough for the graph. Now, I'm not done with number 2. I want to get it in factored form. Well, here, I also want to check out vertex form. Check this out. Vertex form, let's confirm that our vertex would have been, let's see, vertex, I should have done this before, is at 1, negative 3. Yeah, so that confirms our vertex that we got, because this is the HK. I'm speaking on this like you've seen me do it before. You've seen it before. The HK, x minus h squared plus k, the vertex is at 1, negative 3. And that indeed was the vertex we see here, or you see on the point. And the intercepts, let's go ahead and factor this thing down. Let's get factored form. And this one right here, guys, this is straight up common factor scenario. You factor out a 3x, and you're left with x minus 2. Now, if you do 3x there with the x minus 2, this is 3 times x minus 2. Stretch factor is 3. X is one of your factors. Like for zero product property, x equals 0 is one of your x-intercepts, and then x equals 2 is the other x-intercept. So does it cross at 0, 2? Oh, yeah, totally. It crosses at 0, 2. 0, x equals 0 and x equals 2. You know what I mean? So those are the two graphs there. We got it all taken care of. We are squared away. So no matter which form you use, and listen, I'm not asking you outside of this sheet to follow because I want to practice transformations at the same time. I'm not asking you that to graph this. You have to graph it out of standard form if this was a test-based scenario. You know, I'm practicing standard form, I'm practicing conversions, and I'm letting you see that you could have used any one of these to get the exact same graph. All these things give you valuable information. I would honestly probably just graph out of the form that I'm in. So factored form, I just graph out of factored form, but not today. today we're going to standard form. And so to start out of standard form, guys, if you recall, you would go straight from factored form to standard form. Standard form is the intermediary. Everything comes around standard form. So factored and vertex form go up to it, and if I want to do vertex form, I'll go into standard form to kind of get it. But I think the same thing, guys. You could get the vertex from factored form if you know that the vertex is in the middle and plug in the x and stuff. It's just, that's not fully algebra. I guess it's kind of algebraic, but it's not really, it's kind of forcing it. Maybe not. It's kind of forcing it, but that's okay. Let's get into standard form here. And the same thing as I stated before, guys. As far as standard form goes, you can distribute the 2 into one of these, but not into all of these, right? It only does it once. So I always do this first. I would rather FOIL this thing out, just first, outside, inside, last on that, and then distribute the 2 into it afterward. So x times x is x squared, and you got plus 5x minus 3x, so that's plus 2x, and then negative 3 times 5 is negative 15. So now I distribute the 2 into it because, again, standard form has no parentheses. You're not factoring anything out there. I will... Oh, this is factored form. Never mind. Ignore what I was going to say. I was going to say I will get a common factor to factor it, but this is factored form. Okay, so 2x squared plus 4x minus 30. Now, tell you what. Probably not very graphable. I'm looking at this now, so I didn't see this beforehand, so I feel bad in my own right. This vertex is going to be low. You can see the y-intercept is negative 30. I can't fit negative 30 on here. I mean, I'll graph it. I'll change the scales. I'll do it. I'm just kind of letting you know that, this isn't going to be a going by ones kind of thing. I'll change the y's and I'll keep the x's the same. If I change the x's as well, it'll just be a really skinny graph. So I hope you're cool with that when I do this. Our goal is really, I still want you to know what to do to graph out of standard form, get your vertex and stuff like that. So let's go ahead and do that. Let's get the, here's the standard form, 2x squared. I don't really know how to use these boxes when it comes to work. Again, I didn't make this sheet, but I'll just do it here. Vertex, the x value is going to be negative b over, put in parentheses, over 2a, which is negative 4 over 4, which is negative 1. I guess it's not much lower than negative 30, but it's low enough to matter. Oh, I think I can go by 2's. I think it's going to hit negative 32. So I think I can go by 2's. So the y value of this thing is going to be, you plug in negative 1 into here. So 2 times negative 1 squared plus 4 times negative 1, whoops, minus 30 is going to give me negative 1 squared is positive 1. 2 times 1 is 2. 4 times negative 1 is negative 4. And then minus 30. So that's negative 2 minus 30 is negative 32. So your vertex is going to be at negative 1 comma negative 32, okay? Now, once again, your y-intercept here, guys, this is the y-intercept value right there. The y-intercept is 0, negative 30. So I'm going to start by plotting these points right here. Now, when it comes to scale, again, what I'm going to do is I'm going to go by 2's on y. Let me move myself here. I'm going to keep x's the same, so I'm going to give some numbers. This is a 5 still. This is I guess 10 is over here. This is negative 5 and negative 10. All these increments here will go by 2's now. So if this is cool, this is going to be negative 10, negative 20, negative 30. So everything's going by 2's on y. I know I've said it a bunch. I just need to re-remind you what I mean by that. 2, 4, 6, 8, 10, okay? And that's okay. You know why? Because we're doubling our values anyway, so going by 2's means we won't hit any odd numbers, especially because our vertex is also an even number. This is totally okay. And you know what? You got to do this with graphs sometimes, guys. This isn't, I'm yelling at you. Guys, you got to do this with graphs sometimes. Not everything goes by ones. Not everything's a handsome number. Not everything's by the origin. And this is me improvising with that, and I hope you're cool. All right. So our vertex is at negative 1, negative 32. The y-intercept is at 0, negative 30. Okay. Now I'm going to have to remind myself that when I go by 2's that I got to count the 2's, So, all right. Our vertex is down here. It's at negative 1. Remember, I'm going by 1's on x. I'm at negative 1, negative 32 right there. Okay. And 0, negative 30 is right here, which means if I reflect across the axis of symmetry, there should be another point. Now I'm going to start doing my count to go all the way back, up and through. This is going to be a tall graph. I guess it's just as tall as the previous ones before. We'll see. Yeah, it's just, this is, because they're scaled by 2s, it's actually going to look a lot like this one here. So, okay, remember the whole, okay, our stretch factor is 2. If you look back at this here, guys, our stretch factor is 2 and 2, as you can see. So instead of 1, 1, I'm going to go 1, 2. Instead of 2, 4, I'm going to go 2, 8. But remember this, every y value, every increment I go up is a 2. So this is 1, 1, and this is 1, 2 right there. So we're already there. Instead of 2, 4, because this is 4, this is going to be 2, 8. So really, all I'm going to do as far as counting is I'm counting like I normally would. Okay? So instead of 3, 9, it's 3, 18. Well, guess what? That's 9 increments up from here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's really the same thing, only the scales are different. Instead of 4, 16, it's 4, 32. 32 up from negative 32 is that one. Instead of 525, it's 550. What's 50 up from negative 32? It's 18. And you know what 18 is? 18 is 9 up from 9 increments up right there. All right, let's reflect those points. So, you know, you're seeing a lot of the same stuff. The fact that I had to double it is just a, you know, oh well. You know, got to have a conversation with somebody, so hope you don't mind me talking to you. How's your day? Good? All right. All right, and let's... Sorry, I'm only going to do the curve once, even if it's bad. Okay, now I still got to get vertex form from that thing, and it's a good topic of conversation to have. Now, once again, this is probably one of those moments where if it would be better to use the vertex the way that you just found it. The vertex is at -1, -32, and just plug it into the formula. Knowing that your stretch factor is 2. Here, I will show you that, but I need to show you the complete and the square version as well. So, vertex form, check this out. If you know you have H, K, and A, the A is 2, then you can do vertex form. Y equals A times X minus H squared plus K. So I can do that straight up like that. My point, though, is that I want to complete the square to confirm that I can do that correctly and to confirm that I got this correct answer here, right? So here we go. Let's do vertex form by completing the square. Let's take our equation. And here's how you got to do it here. We got to complete the square. We got to factor a 2 out of not everything. The -30 is not involved in the completing the square process. That's going to stay out of the way. I'm going to factor the 2 out of both the first 2 terms right here. Okay. Now I'm going to complete the square. Oh, come on. I'm going to complete the square inside here. And the -30 stayed on the outside. 2 never factored out from it. So whatever I add here, I will also subtract because I'm on the same side of the equation. But I also got to double that value. Because 2 is going to double the value here, then we got to double the value there. It's a conversation we've had before. So I'm just kind of restating it. It's not one we've had a lot, but it's one we've had before. 2 divided by 2 is 1. 1 squared is 1. That's the divided by 2 square process. So whatever I add there, I subtract here. Remember, 2 times 1, 2 times 1. But the whole idea of this one, guys, is this one factors down. That's a perfect square trinomial. So this is 2 times x plus 1, quantity squared. And -30 minus 2 times 1 is -30 minus 2. It's -32. So again, that seems to confirm what we got. Seems to confirm what we got up there. Totally does. So, you know, that's the idea. You can use the HK, you can use -b over 2a to get the vertex values if you'd like to. Make sure you know your a value, plug it in, know your formula. Or you can complete the square and get it. I'm just confirming everything there. And I got the graph in. So that's 3 problems down so far. I got 3 more to go. So hopefully you enjoyed these graphs right there. Remember, these scaled by 2s on y for number 3. All right, here we go. 3 more problems. And this last half should go faster. I know I'm about a half hour in. But now that we've seen them all, we're going to do the same thing. Standard form, vertex form, factored form, and get them all collected. All right, so number 4. I'm sorry, I'm looking at this. Number 4 is not factorable, so I don't know what they want us to do here. Okay, number 4, standard form. The vertex, the x value is at -b over 2a. Why did they give me why did they give me factored form? I like to do these under the pretense that everything's factorable, so apologies. Unless I'm looking at this problem wrong. Excuse me. Negative b over 2a is negative 8 over 4, which is negative 2. All right. The y value, I'm going to substitute the x value into here. 2 times negative 2 squared plus 8 times negative 2 plus 10. Maybe if you want me to change numbers up, if I change this to a negative 10, it would actually be factorable. Is everyone okay with me changing that? Because I'm doing Vertex right now. I have to decide right now whether or not I want to do that. My students have already started working on it. I can't. But it's not factorable. They're going to go, it's not factorable. What do we do? All right, negative 2 squared is 4. Well, you know, here's I guess, part of the talk we should have. Not everything's factorable. So now what this means when it's not factorable also, if it's not factorable, it also means it won't cross the x-axis. You know, that's just a simple, I shouldn't say that. It can cross the x-axis if it's not factorable. If it doesn't cross the x-axis, it means it's not factorable. I know this one will not cross the x-axis because I know what the graph looks like. Therefore, I know. I don't know. I'm pausing too much. I'm sorry. Let's do this. Negative 2 squared is 4. 4 times 2 is 8. And then we got minus 16 there. And then plus 10. Negative 8 plus 10 is 2. So the vertex is at negative 2, comma 2. So you can see right here, the vertex is at negative 2, comma 2. 2 up from the x-axis. And this is a positive upward. Are all these upward facing? No, the last one's not. These are all positive upward facing graphs. Sorry, this one is. It's a positive upward facing graph here. So our vertex is at negative 2, 2. It's not going to touch the x-axis. If it doesn't hit the x-axis, it's not factorable. That's for sure. All right, the y-intercept is also 10 right here. So we know that we're also going to cross at 0, 10. Okay, so let's go ahead and plot that one, and let's do the rest of this graph here. Like I said, I'd rather speed up. I'm sure you will enjoy the conversational pieces here. I'm not even going to draw the axis of symmetry. So I'm going to go, the stretch factor is 2, right? So 1, 2, 2, 8, 3, 18. Doesn't really fit, 18, 19, 20. It would be somewhere, excuse me, up there. I'm just going to give myself a reference point because I like to just get my curve kind of good. But that's really as much as I can fit. Okay, so let's go ahead and get the idea of this graph in there. And again, this one, we can get the vertex form equivalent, but there is no factored form. This one is actually not factorable. And you know what? We are going to run some that are not only not factorable, but do have x-intercepts. We're going to talk about quadratic formula. This is not one of those situations here. I'm just saying that it's going to happen. I didn't anticipate it here because they said put it in factored, you know what form. And furthermore, I don't know if this is a typo or not, but if this was a minus, it would have been factorable. It actually would have. I know the factorization of that one. So, hey guys, factored form's out for this one. You know, apologies to that. Not going to get a factored form here. Well, let's talk about vertex form, and let's confirm that we can get the same vertex of negative 2, 2. So let's factor the 2 out of there, out of the first two terms, right? X squared plus 4x plus blank. And then the 10 never got factored out by a 2, and whatever I add here, I'm going to subtract here. And of course, it's going to be doubled, like this number will get doubled. 4 divided by 2 is 2. 2 squared is 4. So that's plus 4, and then a minus 4, 2 times 4. So this part factors down to x plus 2, quantity squared. And then 10 minus 8. 10 minus 8 is 2. So a bunch of 2's there. 2 plus 2. So your vertex form is going to be that. And does that indeed align with the vertex that we got here? Well, as far as HK goes, that's a negative 2, comma 2, right? And that's negative 2, comma 2. So it all lines up. We're good. All right, so we got that one confirmed, all taken care of. All right, number 5. Let's go ahead and graph, because one more time, guys, this is not factorable. So basically, okay, when it comes to factoring, before I just move on, what I would do is I would start by factoring a 2 out. Oh, you know what? If anything, this isn't good factored form. This is not the factored form they want. But because this doesn't lend you to intercepts. But the best factorization I can get is this, factor a 2 out in there. But the point is, there are 2 numbers that multiply to make 5 and add to make 4. Done. End of story. This is not factored form. This is just a factorization of it. Factored form means you get the intercepts out from it. Okay, number 5. y equals 2 times x plus 1 quantity squared minus 8. So I'm going to get in the standard form first. And like I said, I'm going to expand this assuming it's a perfect square trinomial, how we do perfect square trinomials. So this is square the first term, square the last term, and double the product of x times 1. X squared plus 2x plus 1. And then there's a minus 8 right there. Let's distribute the 2 into these three terms here. We're going to get 2x squared plus 4x plus 2, and then minus 8. And that will be 2x squared plus 4x minus 6. Minus 6 there, okay? So this is standard form. Y equals 2x squared plus 4x minus 6. Ew. Come on. There we go. All right. Show. The vertex. The x value of the vertex will be, and again, I wanted to get into here. We should know what the vertex is going to be, but let's do standard form version. Will be negative b over 2a, which is negative 4 over 4, which is negative 1. By the way, we haven't incurred the wrath, and it looks like we might not. Actually, oh, look at this factor form. This is going to be different. I take back anything I said. I was going to say we might not get fractions and decimals and stuff. Suddenly, I'm not so sure. I didn't look at this one yet, but not so sure. All right, so vertex there is negative 1 for x. What's the y value? Plug in negative 1 into there. 2 times negative 1 squared plus 4 times negative 1 minus 6. Negative 1 squared is 1 times 2 is 2. And then minus 4 and minus 6. Negative 2 minus 6 is negative 8. So your vertex is at negative 1, negative 8. And sorry if I'm going fast. This is just those things. This is where I get to pause and say, by the way, guys, you see vertex form right here would have been negative 1, negative 8 right there. So it looks like at least that's confirmed. That much is good. And by the way, our y-intercept right here is at 0, c. So the y-intercept is at 0, negative 6. And our stretch factor, which I didn't yet mention, is 2. So we can go ahead and graph this one. Let's start at negative 1, negative 8 here on number 5. Negative 1, negative 8's right here. Our y-intercept was 0, negative 6. And of course, I'll reflect that point. And with the stretch factor of 2, we can kind of continue up this process of instead of 1, 1, it's 1, 2. Instead of 2, 4, it's 2, 8. I like that it's actually hitting this. That means it's factorable, you know, and reflect that across. Instead of 3, 9, let's double that. It's 3, 18. So I think that's up at 10. Yeah, that should be. And that's all I can fit. So with that stretch factor of 2, we have liftoff. Whoa! And, you know, the last problem, number 6, is factorable because we start in factored forms. I guess that's good news. Number 4 is the only one that was not good news. But I don't know how tall it is. And even worse, guys, I don't think the vertex ends up being on an integer. Not worse as far as I'm willing to put up with it. I don't care. I'm sure you guys just aren't. All right, factored form. Okay, so for factored form here, guys, this is where we do want to play with the idea of factored form. We do want to play with the idea of common factor of 2. I'm looking right here. Common factor of 2, we have x squared plus 2x minus 3. And now we can factor this thing down. What two numbers multiply to make negative 3 and add to make 2? That is positive 3 and negative 1. So that's our factored form right there. 2 times x plus 3 times x minus 1. Were our x-intercepts at negative 3 and positive 1? Negative 3, positive 1. Yes. Good, trustworthy experience there. All good, all good. All right, one more problem, guys. Number 6. We should, hopefully we're over. Well, I don't know. I don't know what this problem's going to really look like in general. All right, standard form first. Let's distribute everything out here. Let's go. Standard form. Excuse me. I'm going to start with foiling here. I don't like the, I like the 2x. That's right. 2x squared. I like the 2x squared term quantity first. That's okay. 2x squared minus 5x plus 2x minus 5. Oh, this is all multiplied by negative 4. My bad. Let's do that again. 2x squared minus 3x minus 5. 2x squared minus 3x minus 5. 2x squared minus 3x minus 5. Okay. Negative 4 is going to distribute into these three things here, and that's going to be y equals negative 8. Negative 8x squared plus 12x plus 20. Sorry, I hit pause. I was going to state something about the a value. These two a values are different. Therefore, something I want to say. I was going to say that the a value is always the same with these things. Here's the thing. The factored form is a times x minus p times x minus q for a quadratic. What I mean by that is these are 1x's here. You notice how this is a 2x? Well, that means you'd have to force factor out this 2, even if it means fraction in there. So this is not the stretch factor. This is the stretch factor. Your a is -8, guys. This thing is, oh, man. And the 20, by the way, would be out of reach for our thing. I wonder if it's okay if we go by ones. Let's look at what this graph looks like. Let's look at what the vertex looks like. This is not going to be your favorite graph here. I'm sorry, but it won't. And I'm not going to use a calculator for it either. Here we go. The vertex. I didn't make these problems. The x value is at -b. But here's truth to this. Here's truth. You can still, if you have to graph it, you got to graph it, No way around it. This is -b over 2a, which is -12 over -16. That looks daunting, but that reduces to 3/4. Still daunting. I don't love that when it comes to me graphing it, but you know what? We can do what we're going to do. And you know what? We can change. If you wanted to, guys, we talked about changing scales. We can change scales on these graphs however we want. We can change everything to quarters. There's nothing wrong with that. We just got to make sure that we apply everything the same as we move around on it, We don't have to go in between spaces if we don't want to. But we still got to calculate the y value. And that's the part that maybe you're not as much a fan of here. So the y value of the vertex is going to be -8 times 3/4 squared plus 12. And you know what? It might be worth me stating something else that's I want to state a pattern that exists in these next year, because this is part that you might not have so much fun with. All right, 3/4 squared is 9/4. So I'm going to do, 9/16. So -8 times 9/16. Whoa. Plus 12 times 3/4, you do 12. Well, you can do 12 divided by 4. 12 divided by 4, which is 3 times 3 is 9. So plus 9. Plus 20. I didn't expect that. Oh, no, yeah, that's fine. That's fine. I'm sorry. I was thinking of something else in my head. Okay, so -8 times 9/16. I'm doing -8/16, which is -1/2. So -1 times 9 is, so that's -9/2. So -9/2 plus 9 plus 20. Okay, here's where I want to state a trick, because listen, I know you can use decimals, but I want to state a trick here as far as doing these without having to do common denominator. Well, you still have to do a common denominator, but here's the thing. These two are going to add to 9/2. Just those two. There's still the plus 20. But those two alone are going to add to 9/2. When you're plugging in the x value of the vertex in standard form, and we saw this kind of in factored form, there's this kind of weird trick thing that happens to all of them. Have you noticed this for all the other times we did this? I'm going to go all the way back. What's 9 minus 18? -9. Notice how it's the opposite of the first number? What's 3 minus 6? This was the A. This is the A and the B. 3 minus 6, -3. Notice how it's the opposite of the first number? What's 2 minus 4? -2. Notice how it's the opposite of the first number? You see a pattern? What's 8 minus 16? -8. Notice how it's the opposite of the first number? What's 2 minus 4? -2. Notice how it's the opposite of the first number? The first two, when you plug in the x value of the vertex in standard form, these two always combine to become the opposite of the first number. -9/2 plus 9 is 9/2. I just don't take my word for it. Try it for yourself, but it is. All right, 9/2 plus 20. All right, now I need a common denominator. 20 times 2 over 2 gives me 40 over 2. So 9/2 plus 40/2, and that's 49/2. Now, I guess it's important when it comes to graphing what this value actually is, right? That is, okay, yes. I just wanted to calculate that first, but that's going to be 24.5. 24.5. So your vertex is at 3/4, 24. I'm not gonna put 24.5. 3/4, 49/2, which is 24.5. So as far as, you know what, I just don't know I can fit it in my window. I'd be fine graphing at the fractions. I just don't know I can fit it in my window because 24.5 is 7 up from here, and you can say go by 2s, but now we got to do half. You know what? I'll do it. I'll do it. Let's do it. You won't have fun with it, but I will. So 10, we're going to go by 2s. 10, 20, 30. And I want to decide now what I want to go by for my fractions here. Would you mind? Wait, how far does this go over? 3/4? I want to fit some points here. Would you mind me going by? I'm going to go by 1s. I'm going to go by 1s. So 3/4. So if this is 1, wait, 2s. Wait, what's, oh, stretch factor is -8, right? This thing goes sharp fast, doesn't it? I'll go by 2s. Meaning, excuse me, I'll go by halves. So this will be 1. This will be 2. This will be 3. This will be 4. Okay? Now I'm still going to be halfway in between points, and that's the idea. Sometimes you will be. But this will give me a little more width and not make it really... I don't want to make it too sharp either. It's going to be relatively sharp. I don't want to make it sharper than I need to. So here's our point. We're at 3/4. Now 3/4 is halfway between 1/2 and 1. So 3/4 is here. Let me draw the axis of symmetry for you. I think that'll help. So 3/4 is here, guys. Now 24.5 is going to be... Here's 22, here's 24, here's 26. So 25 is halfway in between 24 and 26. Half of that is basically 1/4 of the way up from that. So listen, guys, these really are not good points when it comes to stretch factor business. And I think you have to agree. These are not good points when it comes to stretch factor business. Like, I don't want to put my stretch factor of -8 in this thing of going over 1, down 8, and whatever things like that. If I don't really enjoy my points there. I can. It's just not an enjoyable enterprise. Maybe I could confirm that some of my points are where they're supposed to be. Now, what is another point that I'm supposed to have here? What's my y-intercept? 0, 20. So my y-intercept is 0, 20. So that's this point right here. I can at least reflect that. 1.5 away, 1.5 away. And by the way, really, that's not really 1.5 away. That's 3/4 away, 3/4 away, right? But that's another point that's on the graph there. Now, really, you should only be asked to get 5 points in a graph at minimum. And I think that's what I'm going to do. So you know what I would recommend here? If you could factor it, I'd recommend going into factor form and getting a point. Or I'd recommend plugging points into the table. Just plugging points in the table, see what you get. These didn't have fractions in the problem, did they? No, yeah. So you could plug points into here. Plug points that would reasonably fit. Like I could plug... Whoops, wrong graphs. I could plug in... When x equals, I don't know if that would fit, x equals 3. I think if I plugged in x equals 2, that would fit. Or x equals, -1, which I guess that's the, no, I guess that's a different point. Reflecting it would be a different story as well. So I'm going to do a couple things. I'm going to plug in, let's plug in a value. Oh, what was the standard form? I'm sorry. Y equals -8x squared plus 12x plus 20. Okay, this problem's a lot harder than, for graphing. Right? This worksheet never anticipated graphing. But this problem's a lot harder than it looks when it comes to graphing. What am I doing? I'm going to plug in a value. I'm going to plug in 2 for x because that looks like that can give me a reasonable kind of like, oh, it's going to go, here. I don't know where it's going to go specifically. And I could apply the stretch factor to try some of them. And I think I will later. But let's try 2 for x here. So we're going to get y equals -8 times 2 squared plus 12 times 2 plus 20. You can see why I normally wouldn't go for doing a table. Because it just takes a little while. 2 squared is 4 times -8 is -32. Plus 12 times 2, so that's 24. Plus 20. And that's -8 plus 20, which is 12. So y equals 12. So there's a point on our graph, guys, that's 2, 12. So that's not the vertex or anything. It's just a point on the graph. So here's 2. And here is 12. Hey, I think that's where I said about where it was going to be. Now, there's another point that reflects across, and this is just counting. These aren't the numbers, but 1, 2.5, 1, 2.5 right there. That's another point on this graph, right? Now, I could get the intercepts. I know that's technically cheating and going out of factored form, but just to confirm that our graph is doing what it's doing, guys, because we didn't talk about the intercepts yet, right? If I set this whole thing equal to 0, let me do that in green. If I set that equal to 0, because this is factored form can help us find those, then either x plus 1 equals 0, so x equals -1, that's one of our things, or 2x minus 5 equals 0, add 5 to both sides and divide both sides by 2, x equals 5 halves, and yo, that's 2.5. That's 2.5. So where is -1? That's right here. Now where is 2.5? That's right here. And don't you notice that's the same 1, 2, 3.5 away, and the half, 1.5, 2.5, 3.5 away. So that seems to work as well. So this parabola is kind of doing its thing. If I tried to use the stretch factor, I would totally do this. Remember that going over 1 is every 2. So go over 1 and go down 8. 2, 4, 6, 8. Okay, that would be a point. Over 1, down 8. Right there. And reflect that across. This isn't actually as good as I'd love for it to be. It's about right there. If I went over 2, 1, 2, I'd be going down. Oh, what's 8 times 4? 32? Oh gosh. Where am I at? 24.5? What's 24.5 minus 32? -7.5. So I'd be at 7.5. Wait, shoot, where was I? 1, 2. I'd be at 7.5 down. So 2, 4. Oh, but I was up. Yeah. So I'd be 2, 4, 6, 7.5 right there. That'd be another point. So if I use the stretch factor, guys, these are the points that I'd be getting right there. Not very fun, but it does fall into that graph thing there. Okay, I'm going to complete this graph and finish this video. This is me saying that I've overspoke. People have already probably shut this off and said, this is too hard. And you know what? That is the ambition and joy of saying not every graph is picture perfect. This is the first one where we really didn't get that joyous picture perfect kind of fun. But, oh gosh, that was not well done. But you know what? I did it. I didn't really. Yeah, I'm not really getting that graph done. I'm trying to say, aren't you proud of me, Paul? You know what? I'll take it. All right. And there's the graph for that one. Okay, guys. So, that was number 6. So, oh, you know what? I didn't get vertex form out of this yet. Your goal is to fill out this worksheet, right? So, vertex form. Still not fun. I mean, listen, we already have the vertex, but these are the numbers we're going to get, right? Oh, I'm sorry, you can't really see it. These are the numbers we're going to get, and I'm going to stick with fractions for them. All right, vertex form. We take standard form of y equals -8x squared. Oh, you guys are going to hate me for this. Plus 12x plus 20. You guys are going to hate me for this problem. All right, here we go. I have to factor out the -8 from the first two terms. Yes, even if it leaves me with a fraction here. Now, when I factor this out, that means I divide this by -8. What is 12 divided by 8? That is 3 over 2. So that's subtracting 3 halves x there. And I got to add in a number here. Whatever I add in there, I got to do subtract it from the 20, and it's got to multiply by that -8. No one's listening anymore, but except for math people. All right, I got to divide -3 halves by 2. Dividing something by 2 is the same as multiplying it by 1/2. So -3 halves times 1/2 is -3/4. And now I'm going to go ahead and square that value. And that's easier. 3 squared is 9, and 4 squared is 16. So that's 9/16. And this number here will then be 9/16. And remember, there's that times -8. It's a minus -8 times. So really it's just going to become a plus. I'm going to probably ignore that sign. Now, this part factors down easily for us. We know that -3/4 is the number that goes into the factorization. So this is going to be y equals, there's a -8 on the outside. This is x minus 3/4 quantity squared. And now I have the plus 20 plus, okay, so remember, that's just going to be a plus. 8/16 is 1/2, and times 9 is 9 halves. So 20 plus 9 halves. Hey, we did 20 plus 9 halves before, right here. That's 49 halves. So this is going to be y equals -8 times x minus 3/4 quantity squared plus 49 halves. And that is the vertex form. I'll go ahead and transfer that right up here. There's vertex form. Does that vertex match with the vertex that we achieved over here at 3/4, 49 halves. You betcha it did. No matter what, you got to get the vertex somehow. No matter what, you're going to deal with fractions. Honestly, I would much do negative b over 2a to get that vertex, because here you got to deal with the fraction when you factor out divide by 2 and square it. I'm fine either way. I'm talking about for you guys. I personally would still use negative b over 2a, I guess, especially because I know that those add to be the opposite of that. Okay, guys, so that was a lot of graphing. There was a lot of different transformation things. We confirmed everything that we got there. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Sorry for it getting a little bit, out of the way and cumbersome. I thought 6 problems would go a lot faster, but of course, that number 6, man, that was like a 20-minute killer. All right, guys, this is Mr. Robinson. Thank you so much. Take care.